of like how the planet works. But it would still result in a globe Earth, whether it's retrograde via some sort of other mechanism or retrograde caused by orbit around the sun.
I know, and that's why I don't want to use the atomic model, because I need to go back and study it heavily and modify it to flat Earth, geocentric, and then come back and use his model essentially.
Yeah,
because if I can't, because it's a ball Earth model, but I do like it too. So
yeah,
I don't mind the heliocentric. I don't mind the geocentric. But for me, it's not a sphere, like in nothing. But it's okay. I understand the model well. Like I like it. It's fine.
Yeah, and like you said, like we don't necessarily have to center it on the sun. We could even center it on the Milky Way, and so you've got that same sort of spiraling system, and our own sun is part of that. And like over a very long time, we might eventually get one orbit of this thing. And like I like looking at it from a rotation speed point of view, like in the context of the Earth-Sun system. Like one orbit expressed as an RPM is such a low number, like, and even just the Earth itself, to just the background stars, has a rotation of like 0.0006 RPM, give or take. So either the stars around us have that RPM, or the Earth itself has it. And it seems like the measurements of like mechanical gyroscopes, Foucault pendulums, laser ring gyroscopes are all like detecting that.
That's the drift of the quantum foam. You don't understand where I'm coming from. Hold on, let me write a paper on this first. I got you. I'm gonna take you to the drift of the quantum. Just wait till I'm just gonna hold, like, sit back for 10 years, see what science discovers, and then we'll see then. Or maybe 20. I don't know. There's always cool new stuff.
Well, that's the thing. You're quite welcome to try, and I commend that. Like, it's worth asking questions like, could there be another cause? Even though like the consensus says, or like not like they say, it's like we've got like over 101 different devices planted all over the Earth, and they all seem to indicate like that there is rotation, and you're welcome to try to see if other things are affecting our devices. Yeah, it's a welcome inquiry. Welcome. As highly confident as we are in the understanding that we have, there could be something else affecting it. But at the moment, with the Foucault's pendulum, it seems like latitude changes the independent variable.
Yeah, but the problem with flares is that they basically sit.
Right, which is interesting. But if there is a cause in the precession changed from being clockwise to anti-clockwise, yeah, that's an even bigger problem.
Absolutely. And especially if on the equator you don't have a precession at all.
Yeah. And so, like, I think a misunderstanding of independent variable can lead you to conclude that changing latitude changes the spin. But on a flat Earth, if you change the latitude, I don't think there would be a change or any change on spin, because there's no momentum on a still Earth to cause a deviation in what the pendulum is doing.
Mm-hmm. Yes, I fully agree. But the logic I talked to flares about this many times, and their logic is basically that they don't have to give you like an alternative story to explain why it's happening. If you have a claim why it's happening, then it's only you to prove it. And for them, the only way to prove a cause claim is to actually manipulate the cause. And when you introduce the cause and see that it caused the phenomenon, and when you take away the cause, you can see that the phenomenon disappears, and you obviously cannot do that with the rotation of the Earth. So it's simply a matter of different standard of evidence. Flares have a more extreme one.
Well, yeah. Like,
wait, can I ask you something? Is this a circle jerk server for disappointed globers that they don't have flat earthers anymore?
No, we've got plenty of other topics to talk about.
I'm just saying, like, you all agree on those topics and how are they done. You already know everything that you can expect from flat earthers. So do something new. Talk about the technology.
Dude, just about for a second. Dude, like just 3 minutes ago.
We have it.
Stop looking at the conversation.
Yeah, 3 minutes ago.
I've been the pleasure talking to you, by the way. British guy.
Yeah, I'm from Australia. But I do have the English.
Close enough, right?
Yeah.
I'm just joking, man.
I'm a son of a convict that got ejected from England. I use the eloquence of an Englishman. Yes, I do agree. I prefer eloquence over being a boganist, talking about his shrimp on the barbie. Like, I can go there, buddy. And so it's not a globe Earth therapy session. It's a result of having a nice conversation with somebody who's not sure yet, or who wants to perform more inquiry, and go, sure, you're welcome to try. And so the good thing about understanding things as they are is like, let's do some inquiry, look for some answers. But also we've got these socio-political issues. You've got people in Australia who came here, and there was a culture here, and they weren't agricultural. They went away to the land to find their food. and then they went to another place to find their food. And the difference with agriculture was that we're bringing all this kind of plant life to a particular location and called it a farm. And so like there's a big social change between a culture that goes from hunting and gathering to a culture that goes agriculturally to take the land and put it in a particular location. So yeah, we're definitely happy to discuss other things in regards of helping humans get together on this very real world that we all share. And if we want to be part of the solution, it's most welcome. And that's why
I'm so upset and wants to talk about technology. What is it?
Take the land and put it in a particular location. So yeah, we're definitely happy to discuss other things in the regards of helping humans get together on this very real world that we all share. And if we want to be part of the solution, it's most welcome. And that's why
that's so upset and wants to talk about technology. What is it? I'm sorry. What do you want to talk about technology, Getty?
No, because I was reacting to Imbo explaining for the thousandth time why can't they understand stuff like the focal pendulum. And I said it. I was at that stage years ago. Like, why can't they understand forces? It is very simple. They want to deny any type of knowledge. You will never get anywhere.
Is mass times acceleration next? Like, I'm a flat earther.
Forces.
Force, here you go. That's any force is mass times acceleration, right? You got no acceleration or no mass, you got no forces, right? Right? Wrong?
But anyone knows that?
No.
Not what I mean by flat earthers denying forces.
Okay.
So,
what do you mean then?
So I fully agree with you that flat-earthers just want to deny stuff and they will never understand it because they don't want to. This is what I've been also saying myself since like maybe 2 years already. But I was explaining this because maybe some other globe earthers who are in this voice channel don't know about this. Maybe they genuinely believe that flat-earthers are in good faith and that they don't know all of the tactics they use. And I wanted to explain for those globe earthers who potentially may not know those flat tactics. Not to circle jerk, but because
I hope that's not towards me. Because I am genuinely the person I am on here. I am in real life. I don't really change. Like the other guy came in here. He was an asshole. He shot at me for no reason. I shot back. Like, it depends on how you treat me.
Wait a second. I was just sarcastic and satiric. I know you will forget it in like in half an hour, and someone will come with his observation of the lake, and you will fight with him for the 100th time about reflection, no reflection. It is all good. I know. I'm just kidding.
Yeah, man, I wasn't talking about you. The other guy I think is a flat earther. So.
Yeah, I'm just saying to Imbo and like the TFE killed it, but like and also
talk about science.
And also to you.
I'm in good faith, man. When I'm talking about the gentleman from Australia about quantum mechanics, the dark matter, and all that, it is genuine, like faith, bro. Like, I've told him my position, like, you know what I mean, like straight up,
right?
You know.
But I find it very difficult to believe that someone truly understands you in different physics topics. Why I say forces? Because sometimes when you want to talk about how a plane flies, you should draw it and actually show it what impacts the plane. You can, but I'm talking in general. Like when you're talking to a flat earther, he needs to understand, okay, that overcoming gravity means generating the lift. But you are getting stuck on the gravity side because he wouldn't accept there is a force to overcome.
No, never. I'm never getting stuck here because, like, stress. If you're standing on a piece of concrete and you weigh whatever X amount of pounds and you're not piercing the concrete, which means the concrete is pressing back upon your foot with equivalent force. Okay, whenever that force is not equal, guess what? You're going through the concrete, right? Which means it gave way. It yielded because the stress, which is force divided by area, right? Sigma, yeah, for the engineer guy, agent. So it's stress divided by area. Gives it PSI or pascals.
No, you're butchering.
Forces. No, forces come in pairs. I'm not butchering anything. Like, so
You're
have
butchering
gravity
stuff
down.
and
I'm not
there's no
butchering
need-
shit. I'm explaining science actually as it is from the textbook. Forces come in pairs. Right or wrong? Just one force out of nowhere is imaginary shit, dude. That's not Newtonian mechanics. That's not any mechanics. If you have like buoyancy, if you have a balloon, if you model the FFB pointing upwards, your vector buoyant force, then your down is G, like straight up, like two pairs. There you go. And you see equivalency, right? This is what, so in the study of mechanics, we study statics and dynamics. And the difference is when the forces are no longer equal.
when you're talking to a flat earther, he needs to understand, okay, that overcoming gravity means generating the lift. But you're getting stuck on the gravity side because he wouldn't accept there is a force to overcome.
No, never. I'm never getting stuck here because, like, stress. If you're standing on a piece of concrete and you weigh whatever X amount of pounds and you're not piercing the concrete, which means the concrete is pressing back upon your foot with equivalent force. Okay, whenever that force is not equal, guess what? You're going through the concrete, right? Which means it gave way, it yielded, because the stress, which is force divided by area, right? Sigma, yeah, for the engineer guy, agent. So it's stress divided by area, you know, gives it PSI or pascals, whichever you want.
You're butchering.
Forces. No, forces come in pairs, and I'm not butchering anything. Like, so
you're butchering
gravity
stuff
down.
and
I'm not butchering shit. I'm explaining science actually as it is from the textbook. Forces come in pairs. Right or wrong? Just one force out of nowhere is imaginary shit, dude. That's not Newtonian mechanics. That's not any mechanics. If you have like buoyancy, if you have a balloon, if you model the FFB pointing upwards, your vector buoyant force, then your down is G, like straight up, like two pairs. There you go. And you see equivalency, right? This is what, so in the study of mechanics, we study statics and dynamics. And the difference is when the forces are no longer equal. When you have summation of, like, if you have a bridge and you get cars moving on it, it's got forces trying to break it, but the summation of forces equals zero. The bridge is stronger, right? The minute the forces are greater than the forces that can be reflected by the bridge, it breaks. That means it goes dynamic. It goes into motion now. That's why it was static, because it can resist it. So that's the line between statics and dynamics right here.
The thing
but
is,
I feel like you don't get me, and you don't get my example because you're drifting into explanations that are not necessarily for me to say that I need the flat earther to first agree with me. There is a downward bias or gravity.
Yeah, your explanation is just constantly repeating that flat earthers are stupid and ignorant, which we all already know, so you're not really saying anything new.
Yeah, like a hollow canoe being buoyant isn't the opposite of gravity. Because the buoyancy formula includes gravity, buoyancy can't be the opposite of gravity.
Where did you hear
I don't think I claimed such things. I modeled it correctly based on the fluid mechanics I studied, and if you argue with that, please post your fucking free body diagram and your forces, motherfucker. Let's go to work. Put some numbers on this shit. I can math, asshole. So let's go. Fluid mechanics. You want me to bust out the book and just take you to school? Free body diagram of submerged object.
I guess
FFB is up and G is down. You serious?
Okay.
Wait.
Okay. Can I ask a question of this gentleman?
Come on.
So you understand then that when we use gravimeters to detect underground mass deposits due to minerals, that cannot be due to local buoyancy effects, right?
Absolutely, but I do not know how the device works. But based on what you're saying, no buoyancy involved here. You're detecting some mass anomalies, yes.
Yes, we're detecting mass anomalies by detecting deviations in the gravitational acceleration that we measure. They use different...
So density, essentially, right?
No.
So you wouldn't map the density of local densities in the Earth as you're mapping this with your gravimeter?
The density isn't, but I thought you understood. Sorry, sir, I thought you understood mathematics. Density is not a fundamental property of matter, is it? density is a derived property
no.
of matter, you need to
That
know
is
its
correct.
mass and you need to know its volume. Therefore, yes, we can turn these results into a density map, but we are mapping the mass distribution under the surface, aren't we? That's the fundamental thing
Yeah,
that's
cool.
happening here. Okay,
That's fine with me.
we can discard this density argument, and we can demonstrate that this is mass attracting
Bro,
mass.
I
In
didn't
fact, we
argue
can- we
with
can-
you. I was asking you if they mapped it. Holy shit, relax. I was not saying that
we
you're
can do
mapping
it-
density, motherfucker. I was
Okay,
asking, dude, relax.
I was
Calm
in the
down.
middle of saying something, so I'm going to continue talking as though I wasn't
Carry on.
interrupted. So
Whatever.
if we have one of these instruments, and for instance we change the mass distribution near it, say we put a proof mass above it, we can reduce the downward acceleration measured by the instrument because there is now a mass above the instrument that is attracting the proof mass upwards. So that demonstrates mass attracting mass, does it not?
Sure. I thought we already moved on from that. We weren't talking about that. And those
Okay.
properties are called intrinsic properties that you're talking about, right? I know.
Yes.
I know the difference. Yeah, thank you.
Okay. So what is the dispute about buoyancy? What are you claiming about buoyancy?
There was no dispute.
Okay,
The guy
so-
started off by saying flat earthers deny forces. And I went on
Okay.
to explain how forces come in pairs. And then another guy, the Russian guy, he said, my explanation is whatever because everybody already knows that. I was like, I modeled it correctly according to the fluid mechanics I know. And then you hopped in. So this is how the
Okay.
conversation went in my head.
Well, how do you define a force?
I have three strings of like force, mass times acceleration, m times a. Nice and
Okay.
easy.
So and how do you define acceleration?
Acceleration would be force divided by mass.
That's a circular argument, right?
No, all right, fine, all right. If you don't want it mathematically derived, then it's a change in velocity. Delta v over delta t equals a,
Okay.
sir.
So,
No.
but
All right,
you,
and
but
change in
you
distance
understand,
over
you
change in
understand,
time.
you understand that
Okay.
relativistically, your velocity depends on your frame of reference, and therefore you're saying that forces are frame of reference dependent.
Okay, so you have to put your x and y somewhere.
Yes,
Your
you
so-called
do,
frame of
but this is all I'm asking is because the way a relativist would define an acceleration is that an acceleration is what is measured by an accelerometer. What you're defining as acceleration is coordinate acceleration, which is a different
Correct.
thing from what a relativist means when they say acceleration. So I'm just trying to get a handle on where you're
Okay.
coming from in terms of
So-
defining forces and accelerations.
Tony, I
No
just
worries.
wanted to point out.
The accelerometer on the inside has resistors and a moving mass. Does it not?
Yes,
MEMS
that's correct.
MEMS accelerometer. Okay, so you still do depend on variation of distance, or actually, like electrical resistance that will give you essentially a voltage reading, and you program that to give you a number, because that's how it really actually works.
Yeah, but it's working through inertia, right? So if I drop an accelerometer, I see the accelerometer accelerate in my reference frame, but the accelerometer doesn't register an acceleration, does it?
Correct.
Okay,
should
so the results of the accelerometer are different from what I experience in my reference frame, and that's kind of the point that relativists are getting to.
Okay.
So when you say that there's an equal that forces come in pairs, that's not what a relativist would say.
But
Yeah,
in simple mechanics, equal and opposite reaction. Unless you want to ditch Newtonian mechanics altogether, fine. The conversation.
Well, I mean that is the
Okay,
entire
then.
point. That is the entire
This-
point of. That is the entire point of relativity. Is that Newton's first law of motion is meaningless to a relativist. To say that something that is an object at rest will remain at rest relative to what? Until it is acted on by a force. What are you talking about? Or it will travel in a straight line. Travel in a straight line relative to what?
What?
A relative.
I'm with you.
A relativist will
legit
fundamentally.
The problem you're basically describing, Tony, is the problem that you have to add inertial forces in accelerating reference frames in order to make Newtonian mechanics works. But assuming that you are already working in this paradigm and you can add these forces, then this works perfectly fine, right?
Yeah,
You just have to add forces.
Absolutely, it works. I mean, don't get me wrong. You on the surface of Earth, you can use Newtonian mechanics, absolutely fine, and there won't be any problems with it. And that's why it's such a monumental achievement. I'm just pointing out that relativists come at, and indeed that's my intuitive way of understanding any physical system that I look at. I'm just pointing out that relativists come at it from a completely different perspective.
Absolutely, I fully agree with you on that, but I wouldn't say that necessarily Newtonian mechanics' way of describing those phenomena is inherently incorrect, unless you're describing systems where those discrepancies are huge, like moving closely to the speed of light or next to very large masses. I would say that it's just two different ways of looking at the same phenomenon.
I quite agree, but there are physicists and pedants out there who will fundamentally disagree with you, and I'm not trying. Sorry, I get the feeling now that I've derailed this conversation because it was about something different. So let's get back to the buoyancy thing that you guys were discussing.
I'm trying to say this wasn't even my point, like at all. My point was that most of the conversations can boil up to the reference of if there is even forces acting on objects, which they generally wouldn't agree, and boiling it down to even what does it mean? It means that has an influence on an object which creates a movement. And if we cannot agree upon those definitions of forces acting upon objects, we cannot have the general conversation about anything. That's what I'm talking about.
Right. So when we're talking like a canoe resting on water, we're talking about that canoe is doing something relative to the water and whatever other forces are on it. So when I'm thinking of like a hot air balloon, that's essentially just like a basket with a big, huge amount of cloth over the top, and we're putting our heat into that bag, and it's slightly buoyant because the outside air is different from the inside air for that buoyant balloon. But without that, we cut the strings off. It's basically just a canoe where it just sits on top of the water. So like talking about buoyancy, like if we jump straight to helium balloons, we kind of like skip the steps of like subtle differences in buoyancy, like a hot air balloon or something.
So I'm asking you again, what would happen if you had to give this explanation to a flat earther? Why wouldn't you open like a whiteboard here or share screen and actually draw the forces so we would understand why it goes the way it goes? Or for example, when we talk about the flat plane, why not to draw the flat plane and actually talk about the impacts?
Well, may I respond to that point? Because I think it's more fundamental. So what I think is at play here is that flat earthers can't understand that there are two forces involved. They see the effects of buoyancy and they say, okay, that acts vertically. That must be the same force that pulls things down. And the fact that things have moved up by buoyancy is exactly the same reason why things move up when I lift them, or when planes go up. There is an upward acceleration being applied, or an upward force being applied to the object. That is greater than or equal to the downward force due to gravity. That's all that's happening in buoyancy. There are two forces, and their misunderstanding is that they think that there's one force that's vertical, buoyancy and gravity. And so I don't necessarily think that you need to go to diagrams necessarily. You just need to make the point. These are two forces acting on the same object, just like when you pick something up, there are two forces acting on the same object.
Yeah, and that's why
I'm a flat earther, and I second MHN's idea. Man, diagrams explain it, bro. Like I understand what you're speaking about because I have the diagram in my head, but it's like not everybody does, and it does help to actually post a diagram.
Yeah, because when we're talking about buoyancy being an opposite of gravity, it's difficult to say how that it's true when the buoyancy formula involves gravity, like the buoyant force calculation involves gravity. So even something as simple as like a hot air balloon, it's currently not inflated and all the air is the same. We keep on like changing the pressure difference, and that difference allows the hot air balloon to go higher in the air. So yeah, maybe Tony would be able to describe better like why that buoyancy isn't the opposite of gravity.
Well, so the buoyancy is a force that arrives because of a difference in air pressure. The air pressure at the bottom of the object is higher than the air pressure at the top of the object, and that results in a net upward force on the object. And this applies to all objects, so even objects that are denser than air. If you weigh an object in a medium, in air, and then you weigh it in a vacuum, it will weigh more in the vacuum because there's no upward force on it due to the pressure of the medium. So buoyancy doesn't just disappear in just because you're heavier than air. It is still acting on you. And that's where the formula comes from. The formula comes from calculating the difference in
Rho VG.
Well, it's rho gz. It's rho times gravity times the change in height. Is the change in pressure? Yeah.
Pressure.
That's the pressure gradient. So it's rho g delta v is the change in pressure gradient. Rho g delta z is the change in pressure gradient. And as you say, when you do the force diagram, it turns into rho g, rho minus rho medium, times volume. Yeah.
V times gravity.
So it applies this upward force due to that, but it basically gets its origin from the fact that the atmosphere is hydrostatically ordered, which is to say that the pressure at each altitude is due to the weight of the overlying medium. So it's just like water in that sense. So because of that, that's why air pressure increases as you go downwards, and that's where the buoyancy force comes from.
And I'm guessing that if you had calibrated scales and put them under a meter of water and you weighed the mass on those scales above water and weighed them below, because of what's happening with the water putting on that mass, the scales would read differently?
Yeah, the scales don't measure mass, right? They're measuring a force, so yeah, it would read different.
Scales are measuring a force. You'd need to tear them to remove the weight of the water, but yes, there'd be a buoyant effect. And indeed, ultimately, when the thing is neutrally buoyant in water, it wouldn't register on the scales at all. It would be floating of itself. And so this is where there's a common misunderstanding about buoyancy, where it comes from. And you can talk about ultimately this comes down to the fact that air pressure is due to the weight of the overlying air, and indeed in the ocean, pressure is due to the weight of the overlying material, that is the atmosphere and the water that's above you.
That's how I always understood it. It's the weight of the column of air above you, or fluid, from both water and air.
That's exactly right. And
okay, I agree with you on that.
Okay, so you Syrus, you say you're a flat earther?
Yeah.
Okay. Can I ask you? So, do you agree with the following statement? If I move 69.1 miles or 111.2 kilometers north or south, I have changed my latitude by approximately 1 degree, and I haven't changed my longitude. Do you agree with that statement?
You're on a sphere, yeah.
Well, even on a flat plane. Is that true on Earth? On Earth, let's assume that the Earth is flat. Okay, if I move 69.1 miles towards the North Pole or away from the North Pole, my latitude has changed by approximately 1 degree and my longitude hasn't changed.
Well, how'd you know it moved by 1 degree?
So the well, this is an axiom that I'm trying to establish, but generally that's what we observe in that. Isn't this what we observe in reality?
Yeah.
Okay.
Yeah,
That if we move, so you agree that in reality, when we move this distance, can't we mathematically then demonstrate, then derive a flat Earth distance formula?
Can you? Wouldn't you be driving a sphere? My head.
Oh no.
Well,
Can
no.
I do an explanation just briefly, Tony, before you go?
Sure. Yep.
So if you've got a flat plane with a north central point and you've got circles radiating out, pick one of those circles very far away. And if you go closer by 69 miles, you could call that like 1 degree of separation all the way to the North Pole. So if you went 1 degree closer or 1 degree further away, it just means your concentric circles would be smaller and larger.
I would assume I'm like going up a surface of a cylinder if I'm
Okay.
observing such.
But we can. Okay, well, let's take a step back. So you agree that the Earth is approximately planar, leaving aside second order topographic effects, right?
Yes,
That's your position. Okay, we'll assume that this is true.
Cool.
And you agree that there is a point on this plane that is called the North Pole. Doesn't matter where it is on the plane. I don't care. There's a point on this plane that corresponds
magnetic?
to
True north or magnetic?
True north. True north.
Yeah.
Okay.
Polaris.
Yep.
Right.
Yep. The approximately the ground point of Polaris. Sure. That's
approximately the line that's towards.
Yeah. So now that we've identified that, we can say, so on Earth we observe that when we move 69.1 miles or 111.2 kilometers towards or away from, directly towards or away from this point, our latitude changes by approximately 1 degree, and our longitude doesn't change. Right? Can we say that we observe that? Is that an observation that's true? Yeah. Okay.
Cool.
So I would argue that from that we can mathematically derive a distance formula for any two points on Earth's surface of known latitude. Because do you want to see a diagram of this, or are you happy for me to describe it verbally?
Yeah, go for it. I'm drawing it in my head. If I fail at some point, I'll let you know.
But exactly. So you wouldn't draw it in your head. We need to be the teacher and to draw the flat plane and how it happens.
Well, I don't know, but look, whenever I'm going to model anything, velocity, whatever, I'm XY grid, XY, boom. That's, I mean, it is, just model everything as flat plane. We're only, the discussion changes when we go like, oh, in totality, we stick these flat planes together. Is it a sphere? Is it not a sphere?
And to be brutally honest, sir, I spent most of my PhD so I'm sharing my screen now. Can people see that? So I spent most of my PhD deriving a flat Earth model for a particular geophysical process. And it was a waste of time in the end, but we use flat Earth models all the time because they are extremely mathematically convenient. They're a lot easier to work with, they're a lot easier to visualize, and the math is a lot easier to do. So let me know when you can see my screen.
I'm looking.
Mathematically convenient. They're a lot easier to for a particular geophysical process. And it was a waste of time in the end, but we use flat Earth models all the time because they are extremely mathematically convenient. They're a lot easier to work with, they're a lot easier to visualize, and the math is a lot easier to do. So let me know when you can see my screen.
I'm looking right now.
Okay, so this is the case that I'm saying. So we've got our point P1. It's got known latitude and longitude. If we move 111.2 kilometers due north, we've changed our latitude by approximately 1 degree. So now if we've got 2 points, we can introduce the North Pole, and we can say, okay, we know the distance of point 1 from, we know the distance between point 1 and the North Pole. We know the distance between point 2 and the North Pole, just from our axiom. Now, since all of those lines, or all of the points on those lines, P1 to the North Pole and P2 to the North Pole, well, P1 to the North Pole all have the same longitude, lambda 1, and P2 to the North Pole all have the same longitude, lambda 2. So the angle between those lines is lambda 2 minus lambda 1. So now we have a triangle. We know two sides. We know the angle between them. There's a formula for the length of the third side, and that comes from the law of cosines. If you've got two sides and an angle of a triangle, you can solve for the third side using the law of cosines, which is something we've known for more than 2,000 years. Like Euclid knew this was true.
Familiar with it. That's for triangles that are greater than 90 degrees. I'm sorry. Not right triangles. Not greater than not a right.
It will work for right triangles. I mean, it's in some senses it's a generalization of, if you look at c squared equals a squared plus b squared minus 2ab because gamma. If gamma is 90 degrees, then that last term cancels out and it's just c squared equals a squared plus b squared.
Right.
Yeah, so
for a right triangle, the law of cosines basically equalizes to Pythagorean theorem. So you could say that the Pythagorean theorem is just a special case of the law of cosines if you assume the triangle is a right triangle.
So now we've got and just to clarify, just to sort of make it clear, we do exactly the same thing on a spheroidal Earth. Okay, we've got two sides, we've got the angle between them. We're trying to solve for that distance. We use the spherical law of cosines to solve for that angle of separation, and then the distance of separation is just that angle times 111.2 kilometers. So it's the same thing. It just uses the spherical law of cosines. So it's the same general principle. We construct a triangle. We're solving for the third side. There's a formula for that we get from the spherical law of cosines. Okay, so now we can go into the real world. Here we're looking at Pensacola to Jacksonville, and there's a railway line from Pensacola to Jacksonville. And we can see the latitude and the longitude of both of those. We can calculate the spherical distance formula, which is 533 kilometers. The track separation is 593 kilometers, and the flat Earth distance is 643 kilometers. So the flat Earth distance is inconsistent with the observed length of the train track. It's longer, but the flat Earth distance is the minimum distance. That's the shortest distance on a flat Earth between these 2 points, but it's longer than the track separation, so it's longer than the train track. We can measure the length of this train track. We know how much steel was put into it. We know how long it takes to travel it. So the flat Earth distance formula is inconsistent with the track separation. Similarly, we can go into the southern hemisphere. The spherical distance is 1,242 kilometers. The track distance, track separation is a bad term. That's my bad. I used it and it actually means something else. But the track distance the track length between the 2 points is 1,281 kilometers, and the flat Earth distance is 3,000 kilometers. So the flat Earth distance is again widely discrepant with things that we can actually measure. That's just verification of where we get those track lengths.
Assuming like a track length, like you assumed laid flat, absolutely flat, and adjusted for average.
I haven't assumed anything of the sort. All I've done is I've measured the distance. And even if it isn't laid flat, so it obviously isn't laid flat and straight in this case, okay? Because so if we look at the spherical distance formula, which on a sphere, that's the minimum distance, and the track separation is 60 kilometers longer. And the explanation for that is, well, it's obviously not flat and straight. But that is actually worse for the flat Earth distance, right? Because flat Earth distance, the flat Earth distance formula is bigger than the track separation, and the track separation is not the shortest distance between the 2 points. So that actually makes it worse. Here again, we've got two train stations in Argentina. Argentina. And the track length is about 450 kilometers, and the spherical distance 405, and the flat Earth distance would be more than double that, 1,200 kilometers. And we can do the same with sea voyages, like when Captain Bligh was thrown off the Bounty, he got attacked by natives the first time he tried to land on an island, and so they decided they needed to get back to civilization, and they couldn't risk putting down on land. So they had to calculate how far they had to go, how much food and water they had, and in order to do that calculation, they needed to calculate the distance that they were going to travel. The actual distance that they traveled was 7,000. If they'd been able to go in a straight line, it should have been about 5,600. Obviously, there are lines and there are land masses in the way, so they couldn't travel the shortest distance. But in the flat Earth, it adds a considerable distance. The Shackleton expedition got trapped in the ice near Antarctica. They had to eventually send 4 guys off in a boat to sail from Elephant Island to South Georgia across a sea, one of the roughest seas in the world in the middle of winter. It's actually, April, May. That's the autumn here. We've been using spherical calculations for over 300 years. And the last one that I want to bring up are the length of submarine cables. So there are submarine cables between various continents, such as this one, which is Hawaii Iki, which goes from Sydney to Seattle. The cable length is listed as 13,528 kilometers. The flat Earth distance is longer than that, and that would require that the cable is at unbearable tension, that the cable is pulled taut across intercontinental distances. Here's another one, the Perth Oman, where the cable length is again shorter than the minimum flat Earth distance, and we can go on and on. Examples from Sydney to South America. This is the Humboldt cable, and this is the Umoja cable that's being built between Australia and Africa. And again,
so the cables are shorter and the tracks are longer.
So no, they're both
tracks
shorter.
are shorter.
The tracks are shorter and the cables are shorter. So if you look at this, the cable length is Sorry, let's go up to this one. In all cases, the cable length, the length of the physical object, is shorter than the flat Earth distance. The flat Earth distance is longer, and that's true in the sailing examples as well. That the distance traveled is shorter than the flat Earth distance, and it's true with the train tracks that the tracks are shorter than the flat Earth distance. The flat Earth distance is
How are
always
you
longer.
getting? So the flat Earth distance, how's it measured? Is it like
It's
map?
calculated. It's calculated from the formula we derived. You remember we derived a formula up here for the flat Earth
Okay,
distance.
so based on
agreed.
okay.
Yeah, based on the axiom. So I mean, you can take issue with my axiom, but my axiom, all I used was one axiom.
I agree with it.
Yeah.
I was just trying to figure out what the problem is.
So the problem is that
obviously a problem, right?
Yeah, the problem is that every time we actually, well, not every time, but when we go and actually measure stuff, the flat Earth distance turns out to be demonstrably wrong and inconsistent. So if the flat Earth distance is longer, if the minimum flat Earth distance is longer than the actual length of track, that's a problem for flat Earth, because it means that the flat Earth distance formula is demonstrably incorrect.
So in a way, they don't see too far; they measure too far.
Well, they measure too short. We measure the stuff, and it's too short to be consistent with the flat Earth. And again, with the flights, we can do the same thing with flights. In this case, I've just taken flights from from southern hemisphere things.
So why is it shorter? Because like so from point A to point B, if that was along an arc path, isn't that longer than a straight line?
No.
Why
no.
not?
So there's an illustration for this. Let me just get it.
You know what I mean? Like on a circle, if I have a what do you call it? If I have a
An arc.
It would be a sector.
Arc
So if I had an arc, an arc and a
it's-
sector, then I and two. What is that? A chord? Would that be a chord from the two tangents?
It's called it's a sagitta. Is the technical
That's the term.
name.
Okay.
Yeah.
Cool. So wouldn't the length of that straight line be shorter than that arc? On the circle,
Yes,
right?
the length of the length of the sagitta would be shorter than but that's not the comparison that you should be making. So here's an example from seismology. So this is the flat Earth form. This is the flat Earth. Case, right? You've got 2 points on the surface of some thing, and it's just a straight line between them. And this is the spherical case, right, where the arc is the arc between these 2 points is the same length as the arc here is the same length as this line here, so they're the same. But you can see that if I had 2 points to the side, if I had a point to the side, so say 15 degrees into this, 15 degrees around, actually the radius of the circle around is less than the radius would be on a flat Earth. So if I look at this, if I look at this from above, you see this circle, the radius of that, the distance between 2 points on that circle is longer than it would be if looking from above. Sorry, I'm not expressing this very well. If you've got a planar circle, the distance between 2 points on the circumference of that circle is greater than it would be if that circle